Okay, this exam paper was written in January 2023. I just confirmed. And I'm picking now question one, which contains some of the basics. We have spent some time, but a reasonable amount of time on these kinds of things. So we are looking at question 1.1, 1.2, and 1.3, and we shall do them now. Okay, looking at question one, consider the statement as given there. Okay, the statement is f is greater equal to f of x is greater equal to 0 for all x in the interval. Write down the negation of this statement. Okay, how do we negate this statement? So there is a theorem we use. There's a theorem we use for this negation, and the theorem is as follows. So we then say that the negation of the statement for all x in U, the statement P of x, this is logically equivalent to, by mathematical logic, we first negate the universal quantifier, right? We first negate the universal quantifier, and then now we shall get what we call the existential quantifier. Because this will therefore is the same as that exists. There exists x in U, not P of x. Okay, not P of x. Right, so we know that, not P of x. So this is the theorem we use. Right, so at this point, then if this is the case, we use the theorem, hence the statement can be rewritten. Right, hence the statement can be rewritten in the form we can write that statement in the form we want to negate the statement that says for all x in the interval 2, 4, the statement P of x holds, f of x is greater or equal to 0. So this is logical equivalent to, right, so it is converted to what we call the existential quantifier. So this is therefore the same as there exists. There exists x in the interval 2, 4, open at 2 and close at 4. And then now we negate f greater or equal to 0. So the negation of that is that, so here f of x is not greater or equal to 0. Is not greater or equal to 0, yes. Right, so if it is not greater or equal to 0, it means therefore that f of x is less than 0. It's less than 0. Okay, so that is the statement there. Okay, so That is the answer to the question. So written differently, you can say the negation is that f of x is less than 0 and there exists x in the interval 2, 4. Okay, so that is how we negate this. Now continue solving the next question. Let m and n be positive integers and consider the statement. If mn squared is even, then at least one of m or n is even. Write down the contrapositive of the statement. Okay, we are looking at the contrapositive. Right, I'm going to use mathematical logic for the contrapositive because contrapositive means we have a statement, we have this the statement P implies Q. So it is the same as not Q implies not P. Okay, this is called the contrapositive. You can call it contraposition, but that is what it is called, the contrapositive. Okay, so you just note that one there. Okay, so we have that. We have that. Well, let's use it. Okay, they wanted us to just, so in other words, you can just look at the P here, write down the contrapositive. So you can just look at the P. If this thing here is P, then this is actually implies and this implies, so the whole thing here is Q. So this is P implies Q. So what is the contrapositive? The contrapositive is you start by saying not Q implies not P. So the contrapositive is given by. So you'll say, and also in view of this statement here, so you'll say not at least one of M or N. And then now, yeah, then in mathematics, we say if it's not P or Q, I'm here to give you a lot of these rules, please. It's the same as not P and not Q. In the same way, if you take the negation of the and, this is or, so you can do that for and. Right, so if you take the negation of and, and Q is same as not P or not Q. But I'm mentioning that because now you need to take not Q. So Q is a long thing. So Q is at least one of M or N is even. So you can say if not at least that, then right, then what we get? Okay, then right, then not P, then not mn squared is even. Or this can be written as not this. So this one is two statements now. It's two things. So so now there is an or here. There's an or here. So you can look at this one as a statement, and this one also is another statement. So this one you can call it a statement A. You can call this one a statement B. So what is the negation of this? So it's the same as you are negating like this. Negation of A, well, the first one is the same as the negation of this or that. This or that, P or Q. And then if you negate that one, is the same as not, at least, one of M, and then you just change the or, it becomes and. Not, n is even. Then this one I'm going to keep for now. Mn squared is even. So here's the answer. Okay, here's the answer. So not at least one of M. So what would that mean? Right, so that would mean, what is the, if you negate at least, it becomes not at least. It's the safest way to write it. Okay, you can think of that as at most. You can think of that as at most, but the very correct way to write it is to say not at least. Not at least. Right. Right. So in other words, if you're to say at least A, you can say not at least A.
Can you
Not
say both?
Okay, that's a good question. Can you say both? Right, because you're saying at least one. Right, so obviously if you say at least one of A or B, what does it mean to say at least one of A or B? So, I mean, in mathematics, what does at least mean? Well, it means at least in mathematics means, for instance, if I say at least, okay, if I say by at least two sweets, what does it mean? By at least two sweets. Well, it means by two or more. It means two or more. Okay, so if you're saying at least one, it means one or more. So then you come here and say, if not at least, right, not at least one of, this is the safest way to write it, but there are many ways, as I said. Now, not at least one of M, and not If you say n is even and n is not even, okay, if n is not even, well, it means we're saying it's not even. So somebody can think of this as being something else, because if a number is not even, then it's what? It can mean many things, but the correct way is to say it's not even, and that is the opposite of even. But now, if it's not even, it might be odd. But again, in general, it's not only odd or even numbers that exist. So you have numbers that are neither odd nor even as such. You have, so you need to be therefore very careful, because obviously odd and even mostly applies to integers. Then now you come here and say not mn squared is even. So we are saying mn squared is even and need to negate that. So this means obviously mn squared is not even. Okay, this will be one way to negate the statement, you know. But again, there are many ways to negate this. And there are many interpretations to this, and somebody else can write it differently, but this is sort of the rule, the contrapositive rule I've written here. So P implies Q is actually logical equivalent to not Q implies not P. So that's by and large these. Right, next question. Use a proof by contradiction to prove the following. Right, so first and foremost, we speak about a proof by contradiction, and it's something called a proof by contraposition. I've spoken about the contraposition, and now we're going to speak about the proof by contradiction, and I'm going to give an example as well. Good, even 2 slides. So, right, let's look at these, the proof by contradiction. Right, let's look at the proof by contradiction. Right, we note that now the proof by contradiction is also called, right, it's a proof by assumption. Some people call it a proof by assumption. Or proof by well, so same thing. We use both these. We either in mathematics we either call it a proof by assumption. In particular, I want to say proof by assumption of the contrary. I'm going to just write only this one. So it is called a proof by assumption of the contrary. Right. So a proof by contradiction is sometimes called a proof by assumption of the contrary. Or obviously a proof by contradiction. Right. Right. So this is how we're going to prove the following, right? So we're saying here, if an integer n can be expressed as this one, well, this obviously is another way of saying if n is equal to n1 and 2, where n is greater or equal to 2. You can write n1 and 2 greater or equal to 2. Then at least one of n1 or n2 is less than the square root of n. Right. So obviously, if you say in mathematics, then at least one of this or that, right, it means that one or more of N1 or N2 is less than N. And so, right, I want to speak about well, this is what we do in a proof by contradiction. I want to say here. Proof by contradiction is used when you have the following. So you have proof by right. So you have a proof by we have a statement P implies Q, like this. You have a statement P implies Q, like that. Right. If you have a statement P implies Q like that, what would a proof by contradiction mean? Okay, there's something called a scheme of the proof by contradiction. Right. So for the proof by contradiction, for the proof by contradiction, right. For the proof by contradiction, um, assume P is true and assume not Q. So you assume P is true and assume not Q. That, and then you arrive at a contradiction because you assume assumption of the contrary. Assumption of the contrary. We just assume that we just assume the contrary and arrive at a contradiction. So let's work on this one. Let's do this one. So what do we do here now? What is our P and what is our Q here? So obviously we start by looking at the if a positive integer n can be written or can be expressed as that. So in other words, that is our P, everything here. From there, it's a P. Then at least, so you have Q here. So now for the proof by contradiction, you need to assume the P is true. So assume everything that's given. And then assume not Q. Okay, so there are many ways to do this, but one way, obvious, is to just assume everything that is given there. So you can say, suppose that, or we could use the word assume. Assume that, or suppose that a positive integer n can be expressed as n1, n2, n1 times n2, where n1 is greater or equal to 2, and n2 is greater or equal to 2, n1 not n2, like that. So you assume this. Right. So moreover, what more do we assume here? What more do we assume here? All right, if you suppose that a positive integer n can be expressed as that way, that is the case. And I want us to look at the fact that yeah, full stop here. Suppose also that right, so now we want to just suppose that not at least not at least one of n1 and okay, if you negate or it becomes and, like we discussed before. So not at least one of n1 and n2 right. Because if you look at the fact that they're saying at least, okay, if you are to look at it, you can look at it halfway. At least one of n1, okay, if we're to stop here, at least, okay, if you are to say, for instance, at least n1 is less than the square root of n. At least n1 is less than the square root of n. Right, so the negation of that would be not at least one of n1 and n2. Right, so obviously the negation of the fact that if you come and say n2 is less than the square root of n, what is the negation of this? Or you come here and say n1 is less than the square root of n. What is the negation of this? Okay, we negated that from the very beginning. First question. First question. Right, so to negate this one, to negate n1 less than the square root of n would be n1 greater or equal to the square root of n. And that would be n2 greater or equal to the square root of n. So in other words, the fact that they're saying then at least, so it's like this one. They're saying at least. Hey, let me use a different color. As we break this question down a little bit, I want to take it to our usual way of thinking. So you can come and say at least. Okay, also the fact that you are using one here of n1 or n2 is just really saying at least n1 is actually saying at least n1 or n2 is less than, okay, let me write only less than there. Right, so at least one or n2 is less than that, so you can write it like that. Right, it's the same as the one you can just remove, because if you're saying at least one of that is really saying at least n1 or n2. It's obviously the one is redundant, because if you're saying you are interested in A or B, that's exclusive. So it's either A or B. So it's sort of one of them. So right, so it's actually the same as saying you can just try to cut out the word one and say at least N1 or N2 is less than N. How else can the fact that at least N1 or N2 is less than N? Right, so if you are to say at least N1 or N2 is less than N, it can actually be written as, you can look at a case where, so in other words, it is either N1 is less than N or N2 is less than N. Okay, you come to a house, to a room, and you want to pick, you go to a shop and you want to pick drinks, and you say, you either pick Coca-Cola or Fanta Orange. So it's either you pick Coca-Cola or Fanta Orange. Generally, well, in this case, we don't suspect both. So now, what is the negation of this? Okay, I want to say the following here. So you can come and say, in other words, it's the same as saying, if you say at least one of these, it's even a very stupid way of saying this. So it's actually saying, if you say at least one of these, is really saying N1 is less than the square root of N, or N2 is less than the square root of N. It's the same as this. It's really saying N1 is less than the square root of N, or N2 is less than the square root of N. That is what it means. Right. So, and hence you can come and then say, and then now you can come and negate this one and negate that one. Right. So, and then you can, if you negate these and say N1, you negate it, it becomes N1 greater or equal to the square root of N, and this one becomes N2 greater or equal to the square root of N. Like that. And then the OR becomes AND. And hence now you can say what? Right. So as you said, that to the negation of at least one of, now you can always say at least. If you say at least, you say not at least. Right. So I would like to write it like this here for a purpose, and then I'm going to change it next line. Okay. You can write it using the negation symbol. If you say, suppose that you can write in using the negation symbol the same thing. Right. So you can use the negation symbol. So, and you suppose that not, and then you come and say at least. The same. At least one of N1 or N2 is less than the square root of N. Okay. Now, what do we do here? We come and then we manipulate the rest. So you put a full stop here. You put a full stop there. So you come and say thus. Right. So if you say, you suppose also that not at least one of these, as I indicated, that the truth is, if you say one of that, you can actually come and say N1 and N2. So the fact that at least one is stupid because it's the same thing as saying n1 is less than the square root of n, or n2 is less than the square root of n. And then you negate this one. Already negated that one on the side there. Right, so it's the same as really saying you negate the first one, which means n1 is greater or equal to the square root of n, and then you put and n2 is greater or equal to the square root of n. Okay, thus it follows that. Right, what follows from there? It follows that n1 is actually greater or equal to the square root of n, and n2 is greater or equal to the square root of n. What is then the meaning of this? Okay, remember what we started with? We started with the positive integer n. Want to arrive at a contradiction here. And we said that the positive integer n is equal to this. So we just started with, suppose n is equal to n1, n2. Suppose a number can be written as n1, n2, you can factor it out. If you can factor it out with n1, n2 greater or equal to 2, such that they're not equal, n1 and n2, you suppose, so in other words, you suppose, moreover, that n1 is greater or equal to the square root of n, and n2 is greater or equal to the square root of n. What would this mean? If you multiply these two numbers, n1 and n2, because they are greater, and these are positive integers, all of them. We're dealing with positive integers here. So if you decide to multiply them, n1 and n2, thus it follows that hence n1 and 2, you can multiply them. If you multiply them, okay, you have the greater equal to. Okay, but surely if you multiply them and they are greater or equal to, well, it follows that even this inequality will hold. Think of any numbers that are positive. The problem can be with negative numbers, but with positive numbers, this follows. And then what is the meaning of this? n1, n2 is greater or equal to n. We can write the square root of n like this, and then you square it, which means n1, n2 is greater or equal to n. Okay, so you have n1, n2 is greater or equal to n. So now you need to analyze these and see what this means. So n1, n2 greater or equal to n. What is the meaning of this? Does it make sense from the fact that you started with a positive integer and you got n1 and n2 through factoring? Now n is equal to n1, n2. In other words, you started with n equals n1, n2. Then what you are getting now is that N1, N2 is greater or equal to N. Right, so if N1, N2 is greater or equal to N, how consistent is this with the assumption? Yes, so you need to compare this with the assumption N equals to N1, N2. So obviously, you know that N is equal to N1, N2, and you have N here now, but N is equal to N1, N2. Or similarly, you have N1, N2, but you know that N1, N2 is equal to N. Right, so you'd have N is greater or equal to N. So obviously, we understand that. So N greater or equal to N means N is greater than N, or N is equal to N. In each case, then we understand that N greater than N is not true. We agree that N is equal to N. But also we understand that the N1 and N2 from the assumption, N1 can be 2 or more, N2 can be 2 or more, but they cannot be equal to each other. So now suppose N1 suppose N1 is 2 and N2 is what? Is 3. Okay, they can't be equal to each other and they can have those values there. And therefore, if you multiply them here, you can say there's N1, N2, and you multiply them 2 by 3, you get 6. So at this point, what you're seeing is therefore that the N you're dealing with is 6. The N you're dealing with is 6. In which case, therefore, if N you're dealing with is 6, it might mean here 6 is greater than 6, which is false. Or 6 equals 6. Okay, that is true. That is certainly true. Okay. Now, I want us to come to a conclusion here, but in a very clearer manner. Okay, we note that N1 is false. Since N equals N for all positive integers. For all positive integers. We agree that this is the case. For all positive integers. And thus we have arrived. We have arrived at a contradiction. We have arrived at a contradiction. Right, having arrived at a contradiction, means what? It means that our assumption is so that our assumption is false, so that our assumption is incorrect. So that our assumption is invalid. is invalid. And therefore, it follows that and therefore that statement itself is a true statement as given. And then we then say the result has been proved. Right, so you'd come and say, just that it's long, I'm going, yeah, so hence if a positive, yeah, you can come and say, hence if a positive integer just reproduce exactly the same thing. And hence if a positive integer n can be expressed as positive integer n can be expressed as n1 n2 can be expressed as n1 n2 where n1 is greater or equal to 2 and n2 is greater or equal to 2, where n1 is greater or equal to 2 and n2 is greater or equal to 2, n1 not equal to n2, then at least one of those then at least one of n1 or n2, one of n1 or n2 is less than the square root of n. Okay, this is exactly a statement, so we just state it like this. Okay, so this is just one way to do this, but not really the only way. And there can be many, many other ways to do this question. And it's just that obviously you need to think of the best way to manipulate this. You need to think of the best way to manipulate this. Okay, there are many ways to do these things. Many, many ways to do this. Okay, I want to prove one. I want to give one example. I prepared one example that comes in the exam. Okay, it can come, I've seen it in one exam. I might just do that exam in my next appearance, but I'm gonna do this example. Right, there's something we call Euclid. Euclid. Like in school, we know Euclidean geometry. So Euclid's proof by contradiction is that the square root of 2, okay, I need to write this at the bottom. Right, so Euclid's proof by contradiction is that the square root of 2 is irrational. The square root of 2 is irrational. Let's look at the proof of this. It's an obvious proof. You've seen this normally in high school, but we repeat it now. How do you prove that the square root of 2 is irrational? This applies to a wide range of numbers. You can prove that the square root of 5 is irrational, square root of 3, the cube roots and other things. Right, normally the radicals, and obviously, but it's easier with radicals. Okay, this is just a pattern of reasoning we use here. And we say you suppose it is not the case. It is not the case that the square root of 2 is irrational. Suppose that is not the case that the square root of 2 is irrational. Therefore, the square root of 2 is rational. Hence, the square root of 2 can be represented. Okay. Hence, the square root of 2 can be represented as an irreducible, and write it as an irreducible fraction. That is, they are relatively um, prime integers. Okay, so the integers that are relatively prime with respect to each other. So they're relatively prime integers. Prime integers m and n such that so in other words, the square root of 2 can be written as m divided by n. Okay, so you just assume that it is rational, and it is if the square root of 2 is a rational number, then you can write it as m over n. Therefore, you can square both sides. Getting 2 is equal to m squared over n squared. And if you can do that, and hence we obtain the following, you can cross multiply this, if you like, and get this one. 2n squared equals m squared. Hence, since m squared is 2n squared, it means that m squared is a multiple of 2. Multiple of 2. M squared is a multiple of 2. And one way of saying that is that m squared, I like saying m squared is a multiple of 2. Is a multiple of 2. I like saying these. If you don't want to say m squared is a multiple of 2, you can say, or m squared is even. Okay, so another student can say, okay, I think m squared is even. So that is acceptable. Okay. Therefore, therefore, um, therefore, m must be even, since if it were odd, then m squared would have been odd. Okay. My D is okay. Let me see what's happening here. Okay, we said therefore m must be even, since if it were odd, then m squared um would have been odd. This is true. Full stop. Thus, there is an integer there is an integer a thus there is an integer a such that m is equal to 2a. Okay, the fact that m is even, then it means that it's a multiple of 2. You can write it as 2 times some integer. And then we get the following. Hence, if you square it, it becomes what? 4a squared. Okay. Therefore, therefore, 2n squared. We remember that 2n squared is equal to m squared, which means 2n squared is equal to m squared, and m squared is 4a squared. And the implication is that thus n squared is even. Okay, thus n squared is even. Therefore, n must be even. By the same argument. As above. Okay, so we arrived at the fact that n itself must be even. Okay, it's a bit lengthy, but you can make it shorter. And thus, there is an integer. There is an integer b. You can get an integer b such that n is twice b, because n is also even, so it's a multiple of what? The multiple of 2. Okay, so we're here. Therefore, 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 the fraction m divided by n, which was the square root of 2, yeah, is actually twice a over twice b. Okay, I'm going to give you homework at the end of this on these things. Is not is not irreducible. We okay. I'm going to look at the assumption we made about irreducibility versus reducibility. In other words, this fraction has common factors in both the numerator and denominator, which contradicts our assumption. Which contradicts our assumption. Which contradicts, let me start here. This is the last line. Our assumption. Which contradicts our assumption. Okay, I wanted to say, which contradicts our assumption that m over n is irreducible. We had assumed that it is n over m is irreducible. This contradiction completes the proof. This contradiction completes the proof. Okay, this is just one example I decided to just put together, but the idea is clear, but it can be done in many ways, and one can cut out the rest of the explanations, etc., and be very brief in a couple of lines. It can be proven that the square root of 2 is irrational, and in the same way, you can prove that the square root of 3 is irrational. Square root of 3, square root of 5, square root of 7. All these are irrational, and proof is similar. And the proof of all this is done like this. Okay, so that one is not a problem. And then let's look at the next question. I was looking at these questions. I looked at the January 2023 paper and I realized that okay, this question looks like the 2.1 looks like the one you sent to me a few days ago. So just loaded it here, but I did not quite confirm, but it looked like the one you sent to me. And so I then said, let me just what? Let me just put it here so that I can see if when I get to the discussion, I can just check. I can just check on my records if it is the same thing.
I think we did it. I sent you the this is from the Jan 2023
paper. Yeah, definitely. So yeah, we did the 2 point. We did the 2.1. So I would like us to do, yes, thank you so much. We did the 2.1. So what last, I would like us to do 2.2. Right, so we consider now, so in other words, I put the questions here, so this one was done. It was done. So there's no need for us to do it again. Done in previous, in our previous discussion, so there's no need. It's done in our previous discussion, so there's no need for us to go through it. Right, so we're gonna look at the next one. This one. Right, so how do we do that one? Okay, so we're gonna do that one together now. Right, determine if the inverse exists. Okay, consider the bijection. So the word bijection contains bi in it, and bi means two. Bi means two. Okay. Consider the following bijection. Determine if, okay. Determine if the inverse this one using the fact that I think something is wrong with this question. Something is missing. All right. Either this word is not there. Right. Either they determine the inverse, this using the fact that. Right. Not really saying determine if the inverse. Like, we could say if the inverse exists using the fact that. Yeah. But obviously, this is a bijection. I want to speak about bijection. Bijection means one-to-one onto. Onto means we have a surjection. Okay, we're going to discuss this at some point. Surjection. One-to-one is clear, so it means there is a one-to-one relation. XY, then you have one-to-one. One and that, okay? And then writing clearly, that's not clear. But yeah, you have this. You have these, so you can have P, Q, R, 2, 3. So we have that one is mapped to P, 2 is mapped to Q. So there is a one-to-one map. 3 is mapped to that. So this obviously would just, in a nutshell, describe a one-to-one map. A surjection would mean this would be a surjection, this, in this. So you take P here, and you put 1, 2, 3. XY. They are sets. For every P in Y, so you start from the end. For every P in Y, right, so for every P in Y, there exists a small x, I would say, in big X. If this relation is a function like that, right? So there exists what? Okay. For every P in Y, there exists a small x in X such that such that f of x is equal to some p, where the p is in y. So you really can have this kind of thing. Okay, notice ejection. What would that mean? Okay, I've left a lot. I have lots of screens here. Okay, blank screens. Right, so you can speak of notice ejection, not onto, so not onto. Notice ejection, not onto. Notice ejection, not onto. What is the meaning of this? Okay, that would mean you have X and you have a set X, you have a set Y of the images. This is sort of the domain. And this one would be called the codomain. Right, so in the codomain, you might have a P and a Q. This point is the point P. I'm putting domain points and you map like this. But you realize that when you perform this map, Q is not catered for. Nothing goes to Q. So that does not exist. That does not exist. There is no Y. Just write like that. So there's no X. No X. No X such that. No X such that. No X such that f at X is equal to Q. It's not there. This. Nothing goes to Q. So in other words, the map, if you, okay, I called it F. So this map is not a surjection. It's not what? It's not onto. Okay, now let's look at this question. We're not answering the question. Now I'm looking at the question to mean determine the inverse, G inverse from R to R using the fact that that is the case. Right, so it's easy to do that. So it was a very good hint from the examiner. Thank you, Mr. Examiner. Okay, let me. Hello, Kalisa. Yes, yesterday. I'm so sorry I ran late. So I realized that I was just not gonna make it. So, but I'm gonna be there on Monday for my Monday lessons. Yeah, my apologies because now, yeah, I'm gonna be there tomorrow for my Monday lessons. That's my plan. Yeah, I'm coming tomorrow evening for my Monday lessons. Yeah, for yesterday, my goodness, just that it was scheduled the same day, so my time just could not balance up. I wanted to come through. Oh, yes. Yeah, I will let you know. Yeah, most definitely. Yeah, but I'm planning to be there tomorrow evening for my Monday morning lessons. Okay. Okay, thanks, Kosile. Thanks, goodbye. Thanks, goodbye. Yes, please, my dear. Yeah, please give me a few minutes, my dear. Yeah, okay. Thank you. Um, right, so consider the following projection. Consider the following bijection G from R to R such that G of X equals this. Determine if the inverse G inverse from R to R using the fact that, yeah, determine the inverse. So we're going to determine the inverse using the fact that this is the case. Okay, because this is a bijection, right? If it is a bijection, it means this is true. It means G inverse of X will be the identity map of X, which is X. Okay. So we continue. We continue. All right. Right. So what do we do now? Okay, we just substitute everything here. So in view of the fact that you have that one there, so is going to be G inverse of X. Right, it's going to be G into G inverse of X. Right, so in other words, we replace every X by the inverse. But the understanding is therefore that this result here is equal to X. Right, so we're done with this. So this is X. So which means now the X therefore going to become G inverse of X plus 2 divided by 3 into G inverse of X minus 4. If then you have the here it's going to be G inverse of X is not 4/3. And then here you have 1/3. Okay, this is one way, but there are many other ways of doing this question. But I'm looking at the suggested method and I'm exploring that. You can use this method to but it is true for bijections, this. For maps that are both one-to-one and onto, so you have G inverse of X is the same as 4/3. 4/3. Right, so we have this. Right. Okay, this is what you get. Right, this is what we get. Okay, so we continue. We continue. So this obviously means what? It means X is equal to it means X is G inverse minus 4. The inverse of X is not 4/3. Okay, we just need to solve for G inverse here. So if you cross multiply, it becomes 3x G inverse minus 4x is equal to G inverse of x plus 2, which means G, which is 3x minus 1, is equal to 4x plus 2. Yeah, put 2 pluses there. So we divide. We've just taken one part, and then I'm going to take the other part. Okay, which means you have, yeah, so G inverse is 4x plus 2 divided by 3x minus 1. Okay. Three x minus 1. Right, so in other words, G inverse is that. And so what would this mean for us? So you got that G inverse is that, but also you have also another case. So this second case has to do with the fact that you have 1/3 here. In the second case, so you have that. You have those two parts. That part, or you have that x is equal to 1/3 if G, you can put if, doesn't matter, you can put a comma, but let me just put if to make it clear. Right, billions of ways to do it. X equal to 1/3 if G inverse of X is 4/3. Okay. So you have that. Okay. So the question then becomes, what is the inverse here? I want to also mention the kind of transformation for inverses. From school, this one. Transformation for inverses. So you'd have xy for the inverse, it becomes yx. Okay, what does this mean? I can write this in a very compact manner. Okay, so you have that. Okay, what does this mean for us? Because now we've got this information. What does it mean? It means you swap the roles of the x and the y, and that's what the inverse does. Okay, look, now this one is x. Is x, y. I want to write it nice. Okay, for the second point at the bottom, you just swap the x and the y, so you have that. Very easy. Right, so you have the x and the y. So your x is 4/3 and your y is 1/3. XY. For the inverse, it would mean 1/3 and 4/3, which means yx, which means yx. So this is the inverse. This is the inverse. But also, now I want us to look at this one here. You have the x. X is not 4/3, but it's everything else in R, but it's just not 4/3. And the y, put y, g, which is x plus 2 over 3x minus 4. Okay, obviously, if you swap these, then you'd have um, you'd have that right. So for the inverse, now you'd have the y coming this side and the x coming the other way. Okay. Now it means G inverse of X. This can just be put together, this discussion here. Okay, so you have this. You have this. So what is G inverse? For the top part, we have seen that G inverse is going to be 4x plus 2 divided by 3x minus 1. And this is true, but x cannot be 3, 1/3. X cannot be 1/3 because then it's going to um the denominator is going to be 0. Right. In the second case now, you have another G. Right, which means therefore that we agree that the G of X, G inverse, can be 4/3. Right. So if we agree therefore that G inverse can be 4/3, it can be 4/3 under one thing, that X is 1/3. We agree that X is 1/3. So that's the answer. Okay. So we have used the effect to find the inverse. So this is the inverse. Our next discussion is about Maclaurin. Maclaurin series. Let's discuss Maclaurin. Normally they come in question 5. I've taken the January paper, so we're good. The idea of Maclaurin is a very, very important one, but very, very dear to us. Maclaurin series. This one is just about the repetitive um, about repetitive what? Differentiation. Okay, find the Maclaurin series of the function this. Write in sigma notation. Remember to show that the limit of the R term, the limit of the R term is zero as n approaches infinity. Right, so we start. So now Maclaurin means that x is zero. Means that it's a series about x equals zero, which means f of x. Okay, f primed, which is minus 3e to the minus 3x. F double prime is, okay, use the chain rule. So you just multiply by the derivative of the power of the 3 of minus 3x, and then multiply by the derivative of minus 3x, which becomes 9 e to the minus 3x. Minus 27 e to the minus 3x. Which means f of 0 is 1. Okay, let's do 2 of 0 is 9. 3, 4, 81 e to the minus 3 x is 4, 81. It 2 for 3 minus e to the minus 3x. And this means that you have f to the fifth derivative. If this is pretty much enough, minus 2, 4, 3. Okay. This is what we got. Okay. What is the formula for the Maclaurin series? Here it is. Formula formula for the Maclaurin series. Formula for the Maclaurin series is the is given by n0, f of x is f of 0 plus f primed of 0, x. plus f double primed of 0 x squared over 2 factorial plus f triple primed, so x cubed over 3 factorial. And then you have f fourth derivative of 0 x to the 4 over 4 factorial. Yeah, I stopped at the fourth, fifth, doesn't matter. Okay, so really a little bit much. I wanted us to just to get the pattern right because there's a pattern that normally matches, but this is quite an easy one. Fifth over 5 factorial. And then this thing goes on, this pattern goes on. It goes on to f nth derivative of 0 x to the n over n factorial. So n0 f. What is f0? 1. So you put 1 here. What is f prime of 0? Minus 3. Minus 3x. What is f double primed of 0? 9 plus 9x. What did I do here? Yes. F double primed is 9, but it's x squared over 2 factorial. What is f triple primed? Minus 27. F fourth derivative 81. F the fifth derivative minus 243. Over 5 factorial. Okay. So what is this now? You can see a pattern. Normally there's a pattern and the pattern is clear. So this one is alternating. It is exactly alternating. So you can see it as minus 3 to the power n. Because at 1, x to the n over n factorial. At 1, it is this. At 2, it is 9. At 3, it's negative. At 4, it's 81. At 5, it's minus 253. And so this is sort of the general term, this. So the last one is going to be minus 3 to the power n, x to the power n over n factorial. Okay. So this is, this observation is just that this guy here is the general term. Okay. Now, let me see. Now we can write this in sigma notation, which means Tn0 f of x is actually the summation minus 3 to the power n x to the power n over n factorial, and then it's going to be from n Let me change the variable and use R. Use R here. Right, so you can use R and then use R. Okay, normally we have R and N when it comes to series that are very popular. And then you can take the up to N because it's Tn0. Okay, and this one is R, 1 to 3. Just like that. Okay, let's see how have you answered the question. You can write it like these, but another student can write it like how? You can also write Tn0 f of x, which is n r equals 1. Then you have minus 1. You can write it as minus 1 to the power r. Then you write 3x to the power r divided by r factorial. It can be written like that. Okay, so which is the usual way of writing an alternating series. Okay, so this one is an alternating series. Alternating series. So that for all x such as that is the case, we have that. Okay, we just have to show now that this remainder term here is equal to 0. Okay. We have this. Okay, so here we have the formula. Which is RF n plus 1 of C is minus 1 the power hey, just a second to write something properly here. All right, sorry, you're gonna take one of these. Right, just one sec. There's something I'm just gonna include now here. Okay, sorry. This is what I mean. What is the nth thing? The nth derivative of this? Or in other words, this one here. We normally take it from the nth derivative. Evaluated at x. What is the nth derivative evaluated at x out of this? So f nth derivative. Right, we've seen that it is minus 3 to the power n e to the minus 3x, like this. That is the nth derivative. Because if it is 1, if the derivative is 1, then it's minus 3 to the power 1, minus 3. And then if it's a second derivative, it becomes minus 3 squared 9. The cube becomes minus 27. The fourth power becomes 81, and so on. So good. Okay. So that's what I want. So here, let me first write the nth derivative n plus 1. Well, no, I mean n. Right, I mean n because now I'm just making a mistake there. Okay, because it's the nth derivative we're looking for. We got earlier. Right, so the nth derivative we said is minus 3 to the power n e to the minus 3x. N plus 1, which is minus 3 to the power n plus 1 e to the minus 3x. Okay, the nth plus first derivative is given by that one. Right, so this means for our purpose, it becomes the nth plus first derivative at c, which is minus 3 to the power n plus 1 e to the minus 3x for c at the top, please. On the e, it must be c. Okay, so you put c here, 3, and then you put c here. So 0 less than c less than x, like this. Okay, you have this. Okay. Now this is what we have. Okay, thus the absolute value of this r n zeros, this sort of the remainder term, is the same as n plus 1c. Okay, which is what we've got. And then here it will have n plus 1. You divide everything by um, okay, wait a minute. This is what you have. Okay, then we ask the question I want to, before I write this one, what is the general term of the overall series here? What is the general term of the overall series? Right, so you have this one here. Or if you want to write if n plus 1 c, and then you write x is the n plus 1 over n plus 1 factorial. So that's what it's going to be. N plus 1 factorial. So what is f n plus 1? C. Which is minus 3 n plus 1 e to the minus 3c. And then this is what we get. And then it is multiplied by the general term. So it's x. Okay, let me remove this one. Let's remove the absolute value. And put this here. So here we put x to the power n plus 1. And then we divide everything by n plus 1. Like that. Okay. Now, what is the meaning of all these things? All these here. Okay, you can put absolute value at the bottom, but it's positive at the bottom. Okay, this is what we have. So this here can it be written in a compact manner? Can these be written in a compact manner? Okay, can it be written in a compact manner? Okay, this is what we have. Right, we just need to simplify this and then take the limit of that. Right, so anything that can be done, the n plus 1 and the minus 3, they appear common. So we can group the minus 3 to the power n plus 1. We can group it with x if we like. And the right to the common power. And then that can be divided by the n plus 1 factorial. And then you have the e to the power minus 3c. My point is this can be written as minus 3x is one way. N plus 1 over n plus 1 factorial like this. Then you can multiply it by e to the minus 3c like that. Hey. Since, okay, for purposes of our study, for convergence, we normally take x to lie between 0 and 1. Since c, x lies between 0 and 1, we have c and 1. And so And so 1 plus c bigger than 1. And then we have that. Just 1 second. There's something I want to say here. Okay. Okay. With these, can we be able to take the limits? I need to evaluate. Right, x lies between 0 and 1. So we're dealing with a fraction, and the c is also now lies between 0 and 1, and therefore, what is the limit of this? Now we are in business here. Hence, the limit as n approaches infinity of that okay, which is minus 3x okay. Let's see this one. Well, this one is obvious because now if you compare the as n approaches infinity, the factorial is much larger than the exponential function, but also x lies between 0 and 1. And so it follows therefore that this limit is equal to 0. Then obviously we have to show that this is 0. But obviously I've indicated that the limit of the absolute value is 0. This means the limit, because the limit of the absolute value is 0. So which means n0 so this limit is what? Is equal to 0. So we have dealt with this question. Because the question was like, find the Maclaurin series of the function, write in sigma notation, and show that the limit of the remainder term is 0. So we've written in sigma notation here. And then we had to show that this one can put some brackets here. So we showed that therefore the limit of this is equal to 0. Okay. Right. So we have here another question that's very interesting. This question is about improper integrals. It's about improper integrals. And we shall solve this one. All right. Right. So now there are things we call improper integrals of the first kind and improper integrals of the second kind. Right. So the improper integrals of the first kind and those of the second kind. Okay. Now let's look at these. Right, you can call these the improper integral of the first kind. Improper. Improper integral of the first kind. First kind. Of the first kind. Hey. Okay, obviously said explain why the following integral is improper. The integral is improper. Integral is improper. Means the upper limit of integration. Upper limit of integration is infinity. This one. Now that is the reason why this integral is improper. But you might need to investigate also because there's division by x. But now the only problem with that, obviously x cannot be 0, but 0 is outside this. 0 is outside. Outside the domain of integration. It's outside the domain of integration. Okay. Now, this is what we have. But the only problem could be that a number that is in this interval can make, because this this secant is 1 over cosine. 1 over cosine x. Oh, 5x. So you might need to also check if there is pi over x that is going to be problematic. Okay, because this is the secant squared of pi on x. Okay, let's reason together. When is cosine equal to, when can the cosine be 0, 0? So the cosine is normally 0 at pi over 2 and 3 pi over 2 at 90 degrees or 270 degrees and multiples of that. But all of them are outside because pi over 2 is out, but also pi 2 over 3 is out. Hey, so that is what we have. Hey, that is what we have. Okay, we're finishing this question, please. So in other words, it's improper because of that infinity at the top is the upper limit of integration. But now we cannot have a case where the the integrand is undefined. No, it's not. It's not. There's no case like that. Okay, we've just investigated, thought this out. So we need to, after explanation, explain and then evaluate it. So we can easily evaluate this one. Right, so to evaluate this integral, we always say the integral of 4 to infinity of 1 over x squared of pi over x, dx is equal to the limit, okay, is equal to the limit is equal to the limit you have this. Right. So what is the meaning of these? So you can just let u be pi over x. Du is minus pi over x squared dx. So you can have a table like this. Like this is gonna be pretty much, we're concluding our lesson, please. As we speak about improper integrals of the first kind, but I'm gonna speak about improper integrals of the second kind in our next meeting. So let's see now, this one. I wanted to draw a table like this, and then you have x and the new variable u. X is from 4 to b. U is pi over x, which is pi over 4, and u is pi over x, which is pi over b. So this is what you have. So you have the limit, and then now I'm going to put everything here, but this integral, I'm going to put the limits. This is 1 over x squared u minus pi over x squared dx. So, so the u is going to be from pi over 4 to pi over b. And b approaches infinity. Okay. So this is the limit. Okay, there are many ways to do it, but this is just one way to do the question. So you would have the integral pi over 4. And this one is okay. And this one is pi over b. Made a mistake here. The new variable is u. Right, if the new variable is u, then it means that from this equation here, we're going to get minus, what is the x? It's minus x squared over pi. Du is minus x squared over pi du. So we have this. Hey, so you have the limit as b approaches this. You have minus 1 over pi. The integral of sec squared is the tan of u from pi over 4 to pi over b. Hey, so now we come to this one. So it becomes the limit as b approaches infinity of minus 1 over pi, which is the tan of pi over b minus the tan of pi over 4. So as b approaches infinity, this is minus 1 over pi, which is tan 0 minus the tan of pi over 4. The tan of 0 is 0. The tan of pi over 4 is the same as the tan of 45 degrees, 1. And this integral is 1 over pi. And you're done. And the 1 over pi is the answer. Is the answer. All right. See what else I prepared. I prepared a couple of exercises here that you need to try on the kinds of things we're doing. So now you can just enjoy these exercises. For instance, these ones are just based on the kinds of things we're doing, the methods of proof. Right, so we're saying for each I've taken it from relevant material from the library. Right, for each of the examples of proofs given in this section, determine which steps in the proof above are based on logical inferences which on substantial mathematical arguments and which on substantial, right? Prove the following statements. So that's what I want. Number 2, prove this is 2 in a circle. Okay, I just took a picture of this, so it's not very clear. Clearly indicate the method of proof. Method of proof, proof by contradiction, proof by contraposition, direct proof, and explain the steps. Distinguish the logical from the substantial steps. If the sum of two integers is even, so is the difference. Can it be proven? If a, b, x are real numbers, a less than b, and a less than x less than a into x minus b less than 0, then a less than x less than b. So we're effectively saying if a, b, and x are real numbers, comma a less than b, and the linear term x minus a into the linear term x minus b, the product being less than 0, then x lies between a and b and excluding the endpoints. If a and b are rich, so we have those exercises. H is very interesting. The cube root of 3 is irrational. You need to just prove that in as far as I just gave the example of the square root of 2 being irrational. And I'm going to do corrections to this one in our next meeting. And I'm going to do more additional exam questions on and more practice questions on the other areas. But now exercises 4.8.3 at the end of our lesson today shines a spotlight on the methods of proof. We need to just learn, etc. The direct method, the direct proofs, the proof by contradiction, the contraposition, and things like that. Okay, that is the end. So I must thank you then for joining us today. You're gonna watch this and be able to get started with the proof just at the end of the video. And the rest of our lesson was quite an interesting one. Right, so we are here. Here is where we started, and we are done with the lesson for today. And I must see you tomorrow at the same time, 4:30, if that's okay with you. And I'm preparing more drilling kinds of problems tomorrow and corrections to the exercises at the end of the lesson. Right, and that has taken us to just above 2 hours, so we did quite well. Thanks a lot. I'll see you tomorrow, 4:30 in the afternoon. Okay.